Hey everyone, welcome back to my Calculus 2 series. In today's lesson, we're going to be talking about areas between curves. So firstly, let's remember what the Riemann sum was, and I'm going to link a card back to the video where I talk about Riemann sums and areas under a curve. But just a quick refresher, basically the Riemann sum, it was a summation formula, and what we did in the summation was we said that if we wanted to find the area under the curve y equals f of x, between A to B, what we were going to do is we were going to split up that area into small little rectangles like this, and then we were going to use them to calculate the area under this curve. So the Riemann sum looked something like this. We had I starting from 1 to n, where n would be the number of rectangles, and then we would choose f of xi times delta x, right? And this right here was basically the area of a rectangle where delta x was the width of it right here, and f of xi was the height of the rectangle at the ith x value. So now let's take it a step further and let's see how this would scale to the area in between two curves, right? So before we were taking the area of the rectangle, and we were basically saying that f of xi was the height, right? We would calculate the height from this y equals 0 line and kind of to the height of the rectangle. Essentially, it was something like this, even though we didn't write it, right? It was minus 0. We kind of neglected to write it because it was a 0, so it wouldn't really affect anything. But in this case, the height of our rectangle that we would get over here, right, that is no longer the height of, this should be f of x right here. It's no longer the height of f of x, right? Well, the height of that rectangle happens to be, so if I label this as, let's say, h, the height of that rectangle is going to be f of x minus g of x. And I should probably write xi because we're talking about the ith x. So that would be the height of our current rectangle, right? And, well, delta x would stay the same. The widths would be arbitrary in this case. So now we would get a new formula where we would get the same Riemann sum. However, the height would be changed to f of xi minus g of xi and still times delta x. So we really changed nothing about the formula. It's only the height that differed because the height was now in between two curves. Now, if we were to write this Riemann sum, or use this Riemann sum to write an integral, basically we would have the limit, because we want the rectangles, there to be as many rectangles as possible. This would equal to the integral from a to b of f of x minus g of x, and all of this would be with respect to x, the x variable. So this is the integral that we're going to use to calculate the area in between two curves. Now I'm going to show you another way of kind of how we can think about this integral. If this Riemann sum approach didn't really make much sense, I'm going to show you another visualization of how we can think about the area in between two curves. So let's say that we are given the same question and we are asked to compute the value between y equals f of x, which is this green curve, and then we're going to have the blue curve as being as y equals g of x. So let's say we're asked to compute the area in between these two functions. So essentially the area is going to be here. It's going to be this area, all of this. And we're asked to compute this area. But how are we going to do that? Well, here is my proposal. What we're going to do first is we're going to calculate this entire area, all of the area. Even including this part. So basically we're going to calculate the area like we would if we were to only have y equals f of x as being our only function. So, well, we know how to do that. That would simply be the integral from a to b of f of x dx, right? Just calculating the area under the curve y equals f of x. But then what we want to do is we want to take away this area right here, all of this area right here, because we're not asked to compute that, right? And, well, what is that area? Well, that happens to be the area under the curve y equals g of x between those two same bounds, a and b. So we can simply take away the area from a to b of the function g of x, and then there we go. There is our new formula for calculating this area right here. I'm actually going to put it in red, but it's going to be all of this area, right? It's the difference essentially between those two areas. And as we know, we can use integral properties to kind of convert this integral into one and essentially end up back here. So this is just going to be f of x minus g of x, and then all of this is going to be with respect to x, so dx. And there we go. We have landed at the same two integrals, kind of using two different kind of concepts to get to the same endpoint. So here's the formal definition for the area between two curves. Essentially, if we have a region that is bounded by two curves, so y equals f of x and y equals g of x, and then we have two lines kind of making our endpoints, so x equals a and x equals b, and then obviously f and g are going to be continuous, but the key thing to notice here is that f is greater than g. So f must be greater than g for all x on that interval a to b, which is basically the endpoints that we specified over here. So if that's true, well then the area between all of these lines and curves is going to be given by this integral like we showed in the examples above. Here's an example problem that we could encounter on a test or a quiz or something like that. It's basically asking us to find the area of the region bounded by these two curves, and the sides are going to be x equals 0 and x equals 1. So actually this is a pretty standard problem. I mean, we can just apply the definition that we saw earlier up here. Basically, we know that e to the x is going to be greater than just the function x. And we know that because well, this one grows exponentially and this one grows linearly. So, I mean, it's pretty obvious that e of x is going to be larger than x on this interval. So we know that e to the x will be larger than x. Therefore, we can find the area between these two curves by saying, okay, well, it's the area from 0 to 1. And in between the curve y equals e to the power of x minus just x, because that will be the height of our new kind of rectangle, if that's the way we want to think about it. And now this is a pretty straightforward integral. I'm just going to speed through this, and I'm sure you know how to do this integration. So there we go. We have evaluated our integral, and our final answer is going to be e minus 3 over 2. Pretty straightforward, pretty easy question in my opinion. So now moving on to multiple intersections. There are certain functions that will intersect multiple times, and within those intersections, the function that is larger or greater ends up changing. So as you can see in this case, here's the first intersection, here's the second intersection, and on here, well, the curve, if we label the green curve y equals f of x, then f of x is larger. But on another curve, or sorry, on another interval, on this specific interval, then y equals g of x is greater. So how do we go about computing this integral? This, the definition that we learned, this f of x minus g of x dx, well, this definition relies on the fact that f of x is going to be larger or equal to the value of g of x. However, it's not always the case, especially for this example. So how do we go about computing that? Well, in this case, what we want is we want to calculate actually the absolute value of the difference between these two functions. And I'll show you why. Basically, the absolute value of these two functions is a piecewise function that is split up into two cases. So we have when f of x, or sorry, it's going to be f of x minus g of x when f of x is going to be larger than g of x. Basically, the same definition that we had initially, like up here. However, when g of x is larger than f of x, then we are going to swap the two around. We're going to say it's g of x minus f of x in this case. So again, as you see here, g of x is larger than f of x. That means we're going to use g of x minus f of x. So on this interval here, let me erase these pointers first. On this interval here, we can see that y equals f of x is larger. So we are going to use this part of the piecewise function and say that, okay, on this interval, we're just going to calculate f of x minus g of x. However, on this interval right here, we can see that g of x is larger than f of x. So we're going to use the bottom part of the piecewise function. Now I'm going to run through an example quickly to show you how we could use this in a problem. So here's an example problem that we could see. and it says find the area of the region bounded by the curves y equals sine of x, cos of x equals 0, and x equals pi over 2. So I've gone ahead and used a graphing calculator to basically plot out these graphs, but you could kind of just, like if you can't visualize what they will look like, it's probably better you draw them out. But for example, someone who's worked with them for a while kind of knows that cosine starts at 1. So the cosine of 0 is 1, but the cosine of sine, well, that's 0. So we know on that, the starting interval, cosine is going to be larger than sine, and then eventually sine will be larger than cosine after their point of intersection. And so all that's left to do is to compute the point of intersection, and it's pretty obvious that it's going to be the POI. Basically, when the cosine of x equals to the sine of x, well, that is going to be when x equals pi over 4. Knowing this point of intersection, we know that now there are kind of two separate intervals. So we have this interval right here where I'm just going to shade it in, where the cos is greater, cos being the green one, and then we have this other interval where sine is greater right here. And so the first interval spans from 0 to pi over 2. Or sorry, to pi over 4 to the point of intersection, and on that interval the cos of x is larger than the sine of x. However, on the next interval, so from pi over 4 to pi over 2, right, on this interval, well, the sine of x is larger or equal to the cosine of x. So we need to kind of compute these areas separately and then add them together. And again, we know that the total area under this curve, well, that's going to equal to just from 0 to pi over 2 of the absolute value of f of x minus g of x. Now we can kind of go on to change this. We can start subbing in what f of x and g of x are. So first, let's say that the cos of x is going to be f of x. And then g of x is going to be sine of x. So we're going to end up getting something like this. Now, if you remember, this absolute value basically means that we're going to split up our two kind of cases where one is greater than the other, or the other is greater than the first one. So when cosine is greater than sine, well, we can just take the regular integral. However, this one will only span till pi over 4 because that's the first interval. So on the first interval, we can get rid of this absolute value, and we can just change it to when cosine is greater than sine, and that this integral alone will compute us the area right here on this interval. Now we need to add that second area, and that area spans from pi over 4 to pi over 2. However, sine of x is larger than cos of x, so that is how we're going to calculate this integral, and that will give us this area right here. Now, for these integrals, I'm sure you've seen them a ton, so I'm just going to speed forward, and then we're just basically going to calculate a scalar value. There you go, we have got down to our final answer, and essentially we are done. So the area in between those two curves is going to be whatever the value of that is. I don't know what the root of 2 evaluates to. So this brings us to the last section of today's video, and it's basically integrating using the y variable, or it could be anything else. I just chose to call the section integrating using the y variable because that's what we do when we're dealing with 2D graphs. And basically, some of the times we will have functions that are kind of difficult to calculate, like the area of, if we were to just take like the rectangle as being like this, so upwards, like in this case, it's gonna be really difficult because once we get down to this point, well, the rectangle might be that. We're gonna have to do some like crazy calculation for these like those side rectangles, and it's not really gonna go well. So instead, what we can do is we can kind of flip the way we take the rectangle and instead take it this way. So now all of a sudden, dx that we used to have here is no longer dx. We're gonna be taking dy over here to get the width of that rectangle, and then the height of that rectangle is basically going to be the difference between the green curve and the blue curve. But in this case, it's going to be the x value of the green curve minus the x value of the blue curve. And I'll show you kind of what the integral for this example will look like. So if we have a region that is bounded by curves x equals f of y and x equals g of y, and then we also have these lines kind of bounding it on the side, so it's no longer x equals something, now it's going to be y equals c and y equals d. Obviously f and g are going to be continuous functions, and we're going to have the same restriction that we had before, that f of y is greater than g of y for all basically x's, or sorry, for all y's on that interval. Then this area right here, let me try not to erase everything, this area right here, all of this is going to be represented by this integral, and essentially it's the same thing. However, now we're just going to be using the y variable, so it's going to be f of y minus g of y, and then all of this is going to be integrated with respect to dy. So here's a quick example of how we can apply what we just learned, and it's asking us to find the area enclosed by y equals x minus 1 and y squared equals 2x plus 6. So how can we do that? The first thing to notice is that this is y squared, and we're kind of not used to that, but that's okay. We can still plot it out. So I'm going to go ahead and sort of rearrange this function so that it's in terms of x equals something. There we go, I've rearranged that function, and as you can see we get a quadratic right here. However, the quadratic is now on its side, so it's no longer like this, because a quadratic like that would be y equals x squared. Now the quadratic is x equals y squared, so it'll go something like this. Now as for the other function, we're going to isolate for x as well, and it's pretty simple, just rearranging the terms, and we're going to come to this equation right here. So now we've got both of these equations, and if you don't know the steps yet, I'm going to draw out this graph for you. So basically here is what the graph would look like, and as we can tell, the ends, or like the endpoints of integration, are going to be these black dots right here. But how do we compute them? Well, as we can see, it's the points of intersections between both curves. And how do we find the points of intersection? Well, we set one curve equal to another because we want to check when those points intersect, meaning those both of the curves are at the exact same values. So in this case, I'm just going to substitute this equation into here, and then I'm going to isolate and factor and get both of my x and y coordinates. There we go, we have figured out both of the coordinates of intersections of this curve right here. And now what we can go on to do is to formulate our integral. As we could see, our line x equals y plus 1 is actually going to be greater or equal to the y squared over 2 minus 3 line on this interval between the points of intersection. So now we can go on to start formulating our integral. Essentially, it's going to be the integral from and now we're going to be using the y coordinates of our endpoints, because we're no longer integrating in terms of x's, so we don't care about this like the change in x being here. We care about the change in x or change in y in this case. So we're going to be integrating from the y bounds, meaning from -2 to 4. And because this y plus 1 function is larger than the other one, it's going to be y plus 1, and then we're going to subtract away y squared over 2 minus 3. And all of this is going to be integrated with respect to y. Now if we go on to simplify this integral, it's just going to look something like this. Now this is a pretty easy integral to solve, so I'm going to go ahead and do that now. And there we go, we have computed the area in between these two curves up here. It's going to be 18. So there we go, that's it for today's video on areas between curves. Hopefully you guys enjoyed this video. If this video has helped you out at all, please like and comment as to what I helped you out with. Like usual, if you're new to the channel, please like, comment, and subscribe. It's greatly appreciated. And yeah, I will catch you guys in another video.